Hello friends, I welcome you in lecture number 7 on ring theory. In this lecture, we are going to define another ring with additional properties which is known as a field. So first we recall the definition of a ring. A ring is an algebraic system with two binary operations which we denote by addition and this multiplication symbol. So an algebraic system denoted by R with these two operations is a ring if R with addition operation is an abelian group, and the second requirement is R with this product operation or multiplication operation is a semi-group, and third property is distributive property, that is for all elements A, B, C in a ring R, A dot B plus C equal to AB plus AC and B plus C times A equal to BA plus CA. This is the definition of a ring, and we have discussed this definition in lecture number 1. Now suppose this ring satisfies certain extra conditions with respect to this multiplication operation. R with multiplication is a semi-group. That means if we take any two elements in the ring R, then A into B is also in the ring R, and associative property is satisfied. A into BC equal to AB into C for all ABC belongs to R. So these two conditions make this R with multiplication operation a semi-group. Now suppose this with respect to this multiplication operation, this ring satisfies three more conditions or three more properties. Suppose this ring satisfies commutative property with respect to this multiplication operation, that is A times B equal to B times A for all AB belongs to R. Second requirement is there exists an element denoted by 1 in the ring R such that A into 1 equal to 1 into A equal to A for all A belongs to R. Then this element 1 is called multiplicative identity of ring R. So suppose ring R has an identity. Identity of ring R is considered as identity with respect to multiplication operation. And suppose for every non-zero element, say A, in ring R, there exists another element in the ring R such that A into B equal to B into A equal to 1, and this B is called inverse of element A. So this is true for all elements which are different from additive identity or 0 in ring R. What is meaning of this? Every non-zero element in a ring R has a multiplicative inverse or has an inverse with respect to multiplication operation. So if in addition to these three conditions of ring, if these three conditions are satisfied, then this ring R becomes a field. So field is a ring satisfying these three conditions. First condition is ring R is commutative. Second condition is ring R has an identity, and third requirement is every non-zero element of ring R has an inverse in ring R. And if these conditions are satisfied, then our ring R becomes a field. Now we can observe that in the definition of ring, we require that ring R with multiplication operation is a semi-group, and for field we require these three extra conditions. So you can see if these three extra conditions are satisfied for multiplicative operation, then this R minus 0 with multiplication operation becomes an abelian or commutative group. So if R minus 0 with multiplication operation is also an abelian group, then ring R becomes a field. So we can consider definition of field in this way also, that R with addition operation is an abelian group, R minus 0 with multiplication operation is also an abelian group, and this distributive property. Or we can define field in this way also, that suppose R with addition is a ring, then ring R is a field if it is commutative and every non-zero element of ring R has an inverse in ring R. So these are the different ways of writing the definition of a field. So here I have written this definition of a field. A commutative ring R with addition multiplication which has more than one element such that every non-zero element of R has a multiplicative inverse in R is called a field. Or we can write in this way also, an algebraic system R with addition multiplication operation is a field if R with addition operation is an abelian group, R minus 0 with multiplication operation is also an abelian group, and for any ABC belongs to R, A dot B plus C equal to AB plus AC and B plus C dot A equal to BA plus CA. So this is the meaning of a field, and we can consider some examples also. We are familiar with this set of integers, and we know that set of integers with addition and multiplication operation is a ring. Now if we want to check whether this is a field or not, then first we have to check whether there is an identity with respect to multiplication operation in Z or not. So we know that if we consider product of any integer with 1, then we obtain that integer back. Therefore this ring has an identity 1. 1 belongs to Z is an identity. Now what about inverse? So suppose we consider 2 in the set of integers, 2 belongs to Z, and if we are interested in the inverse of 2 in Z, then we have to find out another integer in Z such that 2 into B equal to B into 2 equal to identity of Z, which is 1. So from this we can see that possible value of B is 1 by 2, but 1 by 2 is not an integer. So there is no integer in the set of integers Z such that 2 into B equal to B into 2 equal to 1. Therefore non-zero elements of this ring of integers, especially 2, has no inverse in ring R. So we can say that every non-zero element of this set of integers is not having inverse in the set of integers with respect to multiplication operation. We can see that only one element 1 or minus 1, these two elements are having inverses, because 1 into 1 equal to 1 into 1, that is 1. So inverse of 1 is 1 itself, because 1 is an identity. And if we are interested in the inverse of minus 1, then also we can see inverse of minus 1 is minus 1 itself. So these are the only elements in the ring of integers which has multiplicative inverse, and they are self-inverses. If we take any integer which is different from plus or minus 1, then it will have no multiplicative inverse in the ring of integers. So ring of integers with addition and multiplication operation is not a field. But if we consider set of real numbers with addition and multiplication operation, then it is clear that every non-zero element will have inverse. For example, if we are talking about 2 in the set of real numbers, then we have to find out B in the set of real numbers such that 2 into B equal to B into 2 equal to 1, and we find that B equal to 1 by 2 is in the set of real numbers. So here every non-zero element will have inverse. If we take any a in the set of real numbers which is different from 0, then 1 by a is also a real number, and a into 1 by a equal to 1 by a into a is equal to identity. Therefore, every non-zero element in the set of real numbers has multiplicative inverse with respect to this multiplication operation. So this R with addition and multiplication operation is a field because R with addition is an abelian group, and if we consider non-zero real numbers, that is R minus 0 with multiplication, then both of these becomes abelian groups, and distributive property is obvious here. So R with addition and multiplication operation is an example of a field ring with extra conditions. Similarly, we can discuss this set of integers modulo 7. We are familiar with this ring, that if we consider Z7, then we have to consider equivalence classes starting from 0, 1, 2 up to 6. And we are familiar with the operations addition modulo 7 and multiplication modulo 7. So we can check that this Z7 with addition operation is an abelian group. We have discussed this modulo group in the lectures on group theory. So you can refer that those lectures on modulo group, and you can check that Z7 with addition modulo 7 becomes an abelian group. Now if we consider Z7 minus this equivalence class 0 with multiplication operation, then this is also an abelian group. That also we can check. We have to check whether it has an identity or not. So here identity element is this equivalence class generated by 1 will serve as identity element of Z7, and we can check that every element of Z7 has multiplicative inverse. For example, if I am interested in the multiplicative inverse of equivalence class generated by 2, then I have to find out another equivalence class such that I obtain 1 here. So that I can find out by trial and error. Suppose I start with 1, then 2 into 1, that is going to be 2. If I start with 2, then 2 into multiplication modulo 7 will be 4, then 2 multiplication modulo 7 applied with 3 is 6, and if I consider 2 multiplication modulo 7 4, that is going to be 8, and if we divide 8 by 7, then remainder is 1. That means inverse of 2 is 4. 2 into 4, this is equal to equivalence class generated by remainder when 2 into 4, that is 8, is divided by 7. So if we divide 8 by 7, remainder is 1. Therefore we find that inverse of 2 is 4. Similarly, inverse of 4 is 2. And in this way you can check for each and every element, every non-zero element of this Z7 has multiplicative inverse with respect to this multiplication modulo 7. Therefore this is going to be a field. If we consider this Z6, then this is not going to be a group. 0, 1, here we have 0, 1, 2, 3, 4, 5 up to 5. So if we want to check whether this is a group or not, then we have to check whether every non-zero element has multiplicative inverse or not. For example, if we check for this element 2 belongs to Z6. Then suppose we start with 1, then we obtain 2. Then if we consider 2 into 2, that is 4. Then 2 into 3, that is 6, and 6 divided by 6 is 0. Then 2 into 4, that is 8. 8 divided by 6 will give us remainder 2. And 2 into 5, that is 10, and 10 divided by 6 will give us remainder 4. So these are equivalence classes, but I am not writing formally. So we can see there is no element in Z6 such that this element gives me identity element. That means this equivalence class, which is different from this 0 of Z6, has no multiplicative inverse in Z6. Therefore Z6 is not a field. And in general, if we have this modulo group, say Zn, or ring of equivalence classes generated by modulo n, addition modulo n and multiplication modulo n, then there is a general result that this ring of integers modulo n becomes a field if and only if this n is a prime number. If n is prime, then only this ring is a field, or this ring becomes field if and only if n is prime. And we have seen that Z6 is not a field because this 6 is not a prime. And here we have seen that Z7 is a field because 7 is a prime number. So in this way we can have this interesting concept of a field, which is a ring with extra properties, or R with addition multiplication operations is a field if R with addition is an abelian group, R minus 0 with multiplication is an abelian group, and distributive property is satisfied. A into B plus C equal to AB plus AC, and B plus C into A equal to BA plus CA. So if you want to prove that given algebraic system is a field with respect to given binary operations, then you have to prove that R with addition operation is an abelian group, R minus 0 with multiplication operation is also an abelian group, and you have to prove these two properties for all elements A, B, C in a ring R. So in this lecture we have introduced another definition, which is a field, and field is a commutative ring which is satisfying this property that every non-zero element of R has a multiplicative inverse in R. Here it is not written that R has an identity, because this property itself requires that R must have an identity with respect to multiplication operation. If R has no identity with respect to multiplication operation, then we cannot talk about inverses of non-zero elements. So this is all about this session. I hope you like it. Thanks for watching.